Hello, I'm Kemal. I will present our paper about calibration of object detectors. Selim, John, and Puneet are the other co-authors. Calibration refers to the alignment of the confidence of a model with its accuracy, and it's essential for the safety-critical applications. Broadly, there are two sets of calibration approaches. Training time approaches produce calibrated models while training, for example using an additional regularizer, and post-hoc approaches map the predictions of a trained model to the calibrated scores on a validation set. While it's extensively studied for classification, calibration has received little attention for object detection, a crucial problem for safety-critical applications. Recently, few training time methods have been proposed. These methods are compared against temperature scaling as the baseline and evaluated using Detection ECE, which measures the gap between the confidence and precision. The accuracy is still measured by COCO-style average precision. In this paper, we first question the evaluation approach used by these methods and identify its important pitfalls. Instead, we introduce a new evaluation approach considering calibration and accuracy together. Second, we tailor Platt scaling and isotonic regression as post-hoc calibrators for object detection. We show that these post-hoc approaches perform 8 D-ECE better than the state-of-the-art Cal-DETR. We begin with the pitfalls of existing evaluation that we identified and how we fix each in this work. While using D-ECE, the detections are thresholded from 0.30, while they are not for average precision. This results in two different sets of detections for evaluation, which is unrealistic. Also, we identify that the Cal-DETR performs the best only for this threshold, so selecting the best model is sensitive to the threshold. To address this, following their practical usage, we evaluate detectors with their operating thresholds. As average precision decreases while the threshold increases, it cannot be used for this purpose. Alternatively, we use LRP error that penalizes both false positives and false negatives, thereby requiring a proper operating threshold for the detector. Second, since the precision is used in existing evaluation, it does not respect to the continuous nature of localization quality, a crucial aspect of object detection. This also results in using binary targets while optimizing post-hoc calibrators. Alternatively, we enforce the confidence to match the average intersection over union of the detections with the ground truths. For false positives, we assume the IOU is 0. This results in more informative confidence estimates compared to using precision. We use localization-aware expected calibration error to capture the overall behavior of confidence scores, and localization-aware adaptive calibration error as the mean absolute error between the IOUs and the predicted confidence. Both measures are minimized when the confidence of the detection is equal to its IOU. In terms of datasets, a domain-shifted dataset is used to obtain temperature scaling as the post-hoc calibration baseline, which is not ideal. To address this, we designed datasets in 3 different settings to enable evaluating calibration of object detectors in different scenarios. Our second contribution is tailoring post-hoc calibrators to object detection. To do so, we first create a calibration set using the detections of a class on the validation set by cross-validating a threshold using LRP error. Using remaining detections, we fit either a Platt scaling or an isotonic regression model, both of which aim to map the confidence to the IOU. They are efficient, easy to use, and applicable to any object detector by preserving their accuracy. Finally, we cross-validate an operating threshold for the detector. We first compare post-hoc approaches on existing evaluation on COCO dataset. We incorporate our approaches into deformable data following existing methods. Our post-hoc calibrators improve state-of-the-art significantly. While the previous best model, Cal-DETR, has 8.7 D-ECE, our approaches decreases it to around only 1. Then we compare the methods using our evaluation framework. And again, observe that post-hoc baseline perform better than all existing methods on in-distribution as well as domain-shifted datasets. Our post-hoc calibrators are easier to use on any off-the-shelf detector compared to training time approaches. To show that, we calibrate 14 different detectors in our paper. Our measures are also easily interpretable, which can be useful to the practitioners. Our calibration tools can easily be accessed from our project page. To conclude, we believe that our evaluation framework will help more reliable benchmarking of the methods. Before training time, we should explore better post-hoc calibration methods for object detection. Thank you for your time.